You know, it's kind of funny how flowing water can be so gentle sometimes,
Yeah,
carving these amazing paths over ages, but then boom, it can just unleash this incredible force.
absolutely. Like those floods we've seen recently,
Yeah.
Colorado, Alberta.
Colombia too, right? Just devastating power.
Yeah.
It really hammers home how much running water shapes everything around us.
It really does. And it's constant, whether it's that slow, steady wearing away or a huge flood event, it's always reshaping the land.
So for this deep dive, we're really going, well, deep into the geology of streams and floods.
Yeah, we've got this whole chapter here packed with information.
Right. We want to get into the core ideas, the processes, the landscapes it creates. Basically, understand how streams work from where they start to, when they really overflow.
And by looking at the whole chapter, we should be able to see the connections, how, like, a raindrop way up on a hill eventually affects a delta or carves a canyon.
Okay, let's start right at the beginning, the source. Where does stream water actually come from? It's not just rain falling directly in, is it?
No, not entirely. Rain and snowmelt are definitely big factors, sure. They can flow into channels or just spread out as sheet wash first.
Sheet wash, like a thin layer.
Exactly, a thin film flowing downhill. But streams also get water from lakes, swamps overflowing, even glaciers melting way up high.
Ah,
And a really key one is groundwater. It can seep out through springs right into the stream, or just generally move from the ground into the channel. The chapter has a good diagram showing all these inputs.
so that sheet wash, that thin film, how does it actually carve out a channel? Seems like it would just spread out.
Well, imagine just a slight dip. Maybe the ground is a bit softer there.
Yeah.
The sheet wash naturally starts to collect in that spot. A little more water means slightly faster flow, maybe. And that starts to erode the soil, the substrate, just a tiny bit.
Ah, okay, concentrating the flow.
Right. And now it's even lower, so it captures more sheet wash. It's like a feedback loop. More water, more erosion, deeper channel, captures more water.
A positive feedback. Makes
Yes.
perfect sense. So how do they get longer? This headward erosion thing. It sounds like the stream's digging backwards.
That's actually a great way to think about it. It's how the stream extends itself upstream towards its source, its head.
How does that work?
Well, two main ways. First, the water flowing into the very top end of the channel still has energy to cut back into the hill.
Okay, simple erosion.
Yeah. But also, groundwater can play a big role through something called sapping.
Sapping.
Yeah, where groundwater emerges, it can make the soil and rock wet and weak. That weakened stuff can then collapse or get washed away easily by the next flow. So the channel effectively grows backward, upstream. You see amazing examples in places like the Himalayas or canyonlands.
Wow, groundwater actually undermining the start of the stream.
Okay, so individual channels form, they get longer.
Mm-hmm.
How do they hook up into those big networks we see?
Well, as a main channel cuts down, the land around it naturally starts sloping towards it, right? Gravity.
So smaller side channels, tributaries, start forming on those slopes, flowing downhill towards the mainstream. They join up, branch out, and over time you get this whole interconnected drainage network.
And the pattern of that network tells you something about the ground underneath. The chapter shows a few different types.
Exactly. The pattern depends a lot on the rock type and the structure of the land.
Like dendritic. That looks like a tree branch pattern.
Yeah, dendros is Greek for tree. That usually forms where the rock underneath is pretty uniform, nothing really forcing the water one way or another, and the slope is gentle, so it just branches out naturally.
Okay. And radial. That's like spokes on a wheel. From a volcano, maybe?
Precisely. Water flowing off a central high point, like a volcano or a dome mountain, creates channels radiating outwards.
Rectangular. That sounds like joins or fractures in the rock controlling things. Streams meeting at right angles.
You got it. Water follows those pre-existing cracks or weaknesses in the bedrock, leading to that blocky right angle pattern.
And trellis. Looks like, well, a garden trellis. Parallel main streams, smaller ones joining at sharp angles.
That's typical in areas with folded rocks, alternating ridges of hard rock and valleys of softer rock. Tributaries flow down the ridges into the main valley streams, which might cut across the ridges through water gaps.
Okay. Last one. Parallel. Steep slopes.
Mm-hmm.
And it can lead to badlands.
Yeah, on a steep, uniform slope, streams tend to just flow straight down, parallel to each other. If the ground is easily eroded, like soft sediments with little vegetation, you get really intense erosion, carving out those rugged, barren landscapes called badlands.
Right. Okay. So we have these networks collecting water. Let's talk scale. Drainage basins and divides. A basin is basically the funnel collecting all the water for one river system.
Perfect analogy. A drainage basin or watershed or catchment is all the land that drains into a specific stream network. And the divide is the high ground, the ridge that separates one basin from the next.
And these can be tiny or huge, right? Local divides, continental divides.
Exactly. The Mississippi Basin, the Amazon Basin, they're enormous. They drain huge chunks of continents. Then you have places like the Great Basin out west.
Which is an interior basin. What's that mean?
It means it's closed off, the water flows in, but it doesn't flow out to the ocean. It just collects in lakes like the Great Salt Lake, or evaporates, or soaks into the ground. It stays within the basin.
Huh, interesting. Okay, the chapter also talks about gaining versus losing streams and permanent versus ephemeral. What's the difference there?
Gaining versus losing is about whether the stream's volume increases or decreases downstream. A gaining stream gets more water from tributaries and, crucially, from groundwater seeping in. That happens if the water table, the level of groundwater, is higher than the streamed.
Okay, water flows in from the sides and below.
Right. A losing stream, conversely, loses water. It might seep out into the ground if the water table is lower, or evaporate, especially in dry climates.
So a river like the Colorado or the Nile could be losing water in dry areas but still flow year-round because it starts with so much water upstream.
Exactly. And that brings us to permanent versus ephemeral. Permanent streams flow all year because they have a reliable source, often groundwater. Ephemeral streams only flow sometimes maybe seasonally or just after a big rain. Lots of streams in deserts are ephemeral.
And the dry channel is called a wash or wadi or arroyo?
Precisely. It's the channel waiting for the next flow.
One last thing in this section. The hyperhaic zone. Sounds technical.
It's a really cool zone, actually. It's the area under and alongside the stream channel where the stream water mixes with the shallow groundwater. Think of it like the stream extending down into the gravel and sand beneath it.
Okay.
The water moves much slower there through all the little spaces, but it's a vital habitat for tiny organisms and important for nutrient cycling in the stream. So the stream isn't just the water you see on top.
A hidden ecosystem right below. Okay, let's shift to how the water moves. Discharge seems key, how much water is flowing past.
Yep. Discharge is the fundamental measure. It's the volume of water passing a specific point per unit of time, usually cubic meters or cubic feet per second.
How do they measure that?
Well, the basic idea is you need the cross-sectional area of the channel, how wide and deep it is, and the average velocity of the water flowing through that area. Discharge is just area times velocity. Gauging stations do this constantly.
And discharge changes all the time, right? Depending on rain, season?
Absolutely. It depends on the watershed size, how much rain or snowmelt there is, whether it's a gaining or losing stream. Even human use like irrigation, you get huge seasonal swings, and flood discharge can be massively higher than normal. The Amazon has the biggest average discharge, by far.
And the speed, the velocity isn't the same everywhere in the channel either. It's slower at the edges.
That's right. Friction with the banks and the bed slows the water down near the edges. The fastest flow is usually near the surface in the middle of a straight channel, away from that friction. Channel shape matters. Too shallow and wide means more friction, generally slower flow for the same volume.
And in a curve, the fast water swings to the outside. That's the thalweg.
You got it. Inertia pushes the faster water to the outside of the bend. The thalweg is that line tracing the deepest part and fastest current, which hugs the outer bank in a curve. You also get the spiral flow pattern in bends, which is really important for how meanders form and move.
Okay, water source, water movement. Now the work it does. Erosion. How does a stream actually break down and remove rock and soil? It's not just pushing, right?
No, though the force is part of it. Gravity gives the water potential energy, which converts to kinetic energy, the energy of motion. And the stream uses that energy to erode in four main ways.
Four ways. Okay. Scouring, breaking, lifting, abrasion, dissolution. Scouring is just picking up loose stuff.
Yep, loose sand, gravel, silt on the bed. The water flow just whisks it away.
Breaking and lifting sounds more forceful, like actually prying rocks loose.
It can be. Especially with turbulent flow, the pressure of the water itself can get into cracks, exert force, and break off pieces or lift clasts from the bed. Hydraulic action, it's called.
Abrasion, like sandpaper. The sediment in the water wears things down. The chapter mentions potholes formed this way.
Exactly. The sediment being carried acts like grip, grinding away the channel bed and banks. Potholes are a great example. Turbulence swirls pebbles around, and they literally drill holes into the rock over time.
And dissolution is just dissolving the rock.
Yeah, water can dissolve soluble minerals, like in limestone, especially if the water is slightly acidic. So the effectiveness of all this depends on velocity, volume, and how much sediment grit the water is carrying. Most erosion happens during floods when all of those are high.
And turbulence helps, that chaotic, swirling motion.
Definitely. Turbulence keeps sediment suspended, maximizing abrasion, and increases the direct force on the bed and banks. It's caused by friction and obstacles in the flow.
Okay, so streams are ripping stuff up. Now they're carrying it downstream. That's the sediment load.
Right. The total amount of material transported, and it's carried in three main ways.
Dissolved load, suspended load, bed load. Dissolved is the invisible stuff, the minerals dissolved in the water.
Correct. Ions from chemical weathering carried in solution.
Suspended load is the fine stuff, silt, clay that makes rivers look muddy.
Exactly. Kept floating by the turbulence. That's why rivers like the Mississippi look brown.
And bed load is the bigger stuff rolling and bouncing along the bottom. Sand, gravel, even boulders in a flood. You mentioned saltation.
Yeah, saltation is that bouncing or hopping motion of sand and gravel. The bigger stuff rolls or slides. It's all part of the bed load, the material moving along the stream.
Then there's competence and capacity. Competence is the biggest particle size a stream can move.
Right. Higher velocity means higher competence. It can move bigger things.
And capacity is the total amount of sediment it can carry.
Yes. Capacity depends on both competence and discharge. A big river might have huge capacity for fine sediment, even if it's not super fast. A flood has both high competence, moves boulders, and high capacity, moves a lot of everything.
Okay, erosion, transport, eventually the stream has to drop this stuff. Deposition. That happens when the water slows down.
Precisely. When velocity decreases, maybe the slope flattens, or the channel widens, or it hits standing water, the stream loses energy, loses competence. The sediment starts settling out.
And heavier stuff drops out first. Sediment sorting.
Yes. Coarser material like gravel gets deposited upstream, or where the flow is faster, while finer sand, silt, and clay get carried further and deposited in slower water. The finest stuff settles out in lakes or the ocean. These deposits are called fluvial deposits, or alluvium.
And they form features like bars in the channel or point bars on the inside of bends.
Exactly. Bars are mounds of sediment in the channel. Point bars are those crescent shapes on the inner curve of meanders where water is slower. And when a river floods and spreads over its floodplain, the water slows way down, dropping silt and mud.
And deltas, where the river meets a lake or the sea.
Right. The velocity drops sharply, and all that sediment builds up a fan-shaped deposit. We'll come back to those specific features.
So a stream changes a lot along its length. The chapter uses Lewis and Clark's trip up the Missouri as an example of this longitudinal profile.
Yeah, it's a great illustration. Downstream, near the Mississippi, the Missouri was wide, slow, gentle slope. As they went upstream, it got steeper, narrower, faster, with rapids, waterfalls.
So if you graph elevation against distance, you get that typical concave up curve. Steep near the source, gentler near the mouth.
That's the classic profile. Steeper gradient upstream means more energy for cutting down, carving valleys or canyons. Near the mouth, the lower gradient favors deposition.
And this idea of base level, the lowest point a stream can erode to, ultimate base level is sea level.
Right. A stream can't cut deeper than the level of the water body it flows into. Sea level is the ultimate limit for most rivers.
But there are local base levels too, like a lake or a resistant rock layer forming a waterfall.
Exactly. A lake acts as a temporary base level for the stream flowing into it. A resistant rock ledge does too, until it's eroded away. Even a larger river sets the base level for its smaller tributaries where they join. These local base levels cause steps or flat spots in the longitudinal profile.
And if base level changes, sea level drops, or the land lifts up, the stream will start cutting down again. Or if base level rises, it deposits sediment.
Precisely. The stream is always trying to adjust to its base level. Tectonic uplift or falling sea level invigorates erosion. Rising sea level or subsidence leads to deposition.
Okay, let's look at the specific landscapes streams create. Valleys and canyons first. The Grand Canyon is the iconic example river cutting down through uplifted land.
An amazing example of downcutting power combined with tectonic uplift. Whether you get a wider valley or a steep canyon depends on how fast the river cuts down versus how fast the walls weather and collapse.
So V-shaped valleys form when downcutting and wall collapse are kind of balanced.
Yeah, the stream cuts down, and mass wasting processes widen the valley walls towards a stable slope, the angle of repose.
But if the river cuts down really fast and hard rock, you get a slot canyon, steep walls.
Exactly. Downcutting outpaces wall retreat.
And the Grand Canyon's stair-step look. That's hard rock layers forming cliffs, softer layers forming slopes.
That's it. Differential erosion. And sometimes, if base level rises, these valleys can fill up with sediment, alluvium. Later, if the river cuts down again, it can leave remnants of that old valley floor high and dry as stream terraces.
Rapids and waterfalls more dramatic features. Rapids are just fast, turbulent water over rocks or steps.
Yep. Rough bed, steep gradient, constricted channel all cause turbulence and rapids. White water is just air bubbles mixed in.
And waterfalls are where it just drops vertically, formed by resistant rock ledges, faults.
Or hanging valleys left by glaciers. The falling water carves a plunge pool at the base.
And they're not permanent, right? Niagara Falls is slowly moving upstream as the rock erodes.
That's the classic example. Erosion undercuts the hard caprock, it collapses, and the falls retreat. Headward erosion in action.
Okay, alluvial fans and braided streams. Alluvial fans are those fan-shaped piles of sediment where a stream comes out of mountains onto a flat plain.
Exactly. Sudden drop in gradient, water spreads out, slows down, dumps its sediment load.
And braided streams, lots of channels, gravel bars, happens when there's way more sediment than the water can easily carry.
You got it. The channel gets choked with coarse sediment, especially after floods. The water splits into multiple, shifting strands weaving between gravel bars, common near glaciers or in deserts.
Now for the classic winding rivers, meandering streams and their floodplains, like the Mississippi.
Right. These snake-like curves dominate low-gradient landscapes. The fastest water erodes the outer bank, the cut bank, and slower water deposits sediment on the inner bank, the point bar.
So the whole meander loop migrates sideways and downstream over time.
Yes, they grow and shift. Sometimes the loop gets really tight and the river cuts across the narrow neck of land, a cutoff.
Creating a straighter channel and leaving the old loop behind as an oxbow lake.
Exactly, if it holds water.
Yeah,
or just an abandoned meander if it dries up. Interestingly, the evolution of land plans helped stabilize banks and made these meandering patterns more common geologically.
And the floodplain is the flat area beside the river that gets flooded.
Yes, bounded by higher ground or valley walls called bluffs. During floods, water spreads out, slows down, and deposits fine sediment.
And natural levees, those ridges right along the banks.
Formed during floods, too. As water just overtops the bank, it slows down immediately and drops the coarsest part of its suspended load right there, building up low ridges. This can actually lift the main channel above the floodplain, like near New Orleans.
Which leads to Yazoo Stream's tributaries trapped in the floodplain, flowing parallel to the main river.
Yep, blocked by the natural levees.
Okay, finally deltas. Sediment dumps where a river meets a lake or ocean.
Right. Velocity drops to near zero, sediment settles out, building land outwards. The river often splits into smaller channels called distributaries across the delta surface.
And the shape depends on the river versus waves and tides. Nile is a triangle, Mississippi is a bird's foot.
Exactly. It's a balance between sediment supply and the energy of the receiving basin. Deltas are also prone to subsidence. The weight of the sediment causes the ground to sink, so continuous sediment supply is needed to keep the delta plane above sea level.
And human interference, like building levees upstream, messes that up. Starves the delta interior of sediment.
Big time. That's a major issue for places like coastal Louisiana. Deltas also naturally shift position over time through avulsion when the river suddenly switches course to a shorter, steeper path to the sea.
Okay, so streams shape the land dramatically. How did these landscapes evolve over really long timescales? The chapter talks about beveling topography, mountains getting worn down to flat plains, peneplains.
That's the idealized long-term cycle. Uplift creates mountains, rivers carve deep valleys, then over millions of years, erosion and mass wasting gradually lower the relief, widen valleys, until you potentially end up with a nearly flat plain close to base level, a peneplain.
But reality is usually more complex. Tectonics keeps interfering.
Exactly. It's a useful concept, but rarely fully achieved before something resets the cycle, like renewed uplift.
Stream piracy sounds cool. One stream stealing another's water.
It is. Headward erosion by one stream can cut into the channel of another, capturing its flow. The downstream part of the captured stream might just dry up. We've seen this happen recently, like with the Slims River in Canada.
And drainage reversal. The whole river system changes direction, like the Amazon flipping from flowing west to east because the Andes rose.
A massive example of tectonic control. Tilting the entire continent can completely reroute major rivers over geological time.
Stream rejuvenation is when a river starts cutting down again into an old, low-relief landscape. Maybe base level dropped or the land rose.
Right. Signs of rejuvenation include stream terraces, remnants of old floodplains left high above the new river level, and incised meanders.
Incised meanders, where a winding river cuts down deep into bedrock, keeping its twisty shape, like the goosenecks of the San Juan River.
A spectacular example. The river was meandering on a flat plain, then rejuvenation happened, and it just carved those meanders straight down.
And superposed versus antecedent streams. Both cut across mountains they seemingly shouldn't.
Superposed streams started on a higher, younger layer of flat rock that buried older, folded structures. As they cut down, they just kept their original path, slicing through the buried ridges.
Okay. An antecedent?
Antecedent streams were there before the mountains started rising. They managed to cut down just as fast as the land was uplifting, maintaining their course right across the growing range. If uplift is too fast, though, the river gets diverted.
Amazing how rivers record that history. Okay, shifting gears to the destructive side again. Raging waters, floods, an inevitable catastrophe, the chapter says.
They really are a natural part of river behavior. A flood simply when the river's discharge exceeds the channel's capacity and water spills onto the floodplain.
Caused by heavy rain, snowmelt, dam breaks. The chapter splits them into slow-onset and flash floods. Slow ones build up over days or weeks. Seasonal floods.
Right. Like major river system floods from prolonged rain or snowmelt, or flooding on large delta plains. Think of the huge historical floods in China, or the Mississippi floods of '93 or 2011. There might be time to prepare, but the scale of damage can be immense. Atmospheric rivers can cause these too.
Flash floods are the sudden, dangerous ones. Minutes or hours.
Yeah, often from intense thunderstorms or dam failures. Very little warning time. Especially dangerous in narrow valleys or canyons where water rises incredibly fast, can happen even in deserts. The Big Thompson flood, Johnstown flood, tragic examples.
The sheer force is terrifying, carrying debris, mudslides.
Yeah, exactly. Incredibly destructive and life-threatening.
And then there are glacial torrents, like the Missoula floods, ice dams bursting.
Some of the biggest floods known on Earth unleashed truly colossal amounts of water when glacial lakes suddenly drained, carving landscapes like the channeled scablands in Washington state. J. Harlan Brett's figured that out.
Incredible scale. So inevitably, humans try to control floods. Dams, levees. Mark Twain said the Mississippi was untamable.
We've certainly tried. Dams store water. Levees try to confine it. The Mississippi system was heavily engineered after the 1927 flood.
But even that didn't stop the 1993 or 2011 floods entirely.
No. Reservoirs filled up. Levees were overtopped or failed. Levees can fail by undermining two water pressure forces a path underneath them, leading to collapse.
So sometimes they have to make tough choices, like intentionally breaching levees in some places to save others, like they did in 2011 along the Mississippi.
Yes, diverting water into designated floodways or less populated areas. But it highlights the limitations. Levees confine the river, which can actually raise flood levels downstream, and building them high enough everywhere is incredibly expensive and doesn't eliminate risk.
Oh, so now there's more focus on other approaches, working with the river.
Exactly. Things like restoring wetlands to absorb water, establishing floodways where building is prohibited, maybe even relocating vulnerable communities, moving away from just trying to fight the river.
How do we assess the risk? The chapter talks about annual probability and recurrence interval, the 100-year flood idea.
Right. The key is that a 100-year flood doesn't mean it happens only once a century. It means there's a 1 in 100 or 1% chance of a flood that size or larger happening in any given year.
Ah, okay. So you could have 200-year floods close together, statistically speaking.
Absolutely. Annual probability is a clear way to think about it. FEMA maps show zones based on these probabilities, like the 1% annual chance flood zone. The big Nashville flood in 2010 was estimated as roughly a 0.2% annual probability event, a 500-year flood.
Understanding that probability is crucial for planning. Okay, the final sobering section. Vanishing rivers. Environmental problems.
Yeah, rivers are vital, so we settle near them, but we also put immense pressure on them.
Pollution is a huge one. Sewage, industrial waste, farm runoff.
Toxic chemicals, fertilizers, animal waste, even just trash. It degrades water quality, harms aquatic life, contaminates sediment, a massive problem globally.
Dams, too. Good for power and water supply, maybe, but bad for fish migration, natural sediment flow.
Right. They fundamentally alter the river ecosystem, trapping sediment needed downstream for floodplains and deltas, blocking fish, destroying wild river character.
They're just using too much water for cities, farming, industry.
Huge demand. Agriculture is the biggest user globally. Rivers like the Colorado are so overallocated that they often dry up before reaching the ocean now.
And urbanization and farming change how water runs off the land, too.
Definitely. Cities replace absorbent ground with concrete and asphalt. Rain runs off much faster. less soaks in. Storm sewers channel it straight to streams. This increases peak flows, causes more flash flooding. The chapter shows hydrographs illustrating this: sharper peaks, less lag time after rain.
And farms. Less vegetation than forests, especially in winter.
Right. Can lead to more runoff, and that runoff carries away soil, increasing the sediment load and pollution in streams.
Wow, so many interconnected issues. Okay, well, that was definitely a deep dive. We've covered the whole journey of running water.
From how streams get started with sheet wash and groundwater sapping,
Through the different drainage patterns, how discharge and velocity work.
the ways streams erode, scouring, lifting, abrasion,
So
dissolution,
they carry sediment, dissolved, suspended, and bed load, competence, and capacity.
where they deposit that sediment, bars, point bars, floodplains, deltas,
How their profiles change, the role of base level.
the incredible landscapes they carve: V-shaped valleys, slot canyons, waterfalls, alluvial fans, braided streams, those amazing meanders and oxbow lakes.
How landscapes evolve over time with piracy, reversal, rejuvenation, incised meanders.
The different types of floods, their causes, the devastation they bring.
Our attempts at flood control, the challenges, and newer strategies.
And finally, the serious environmental threats our rivers are facing from pollution, dams, overuse, and land use changes.
Yeah, we really hit all the key concepts, processes, and features from the chapter. It shows how everything connects the geology, the water cycle, the landscape, and us.
Absolutely. Understanding how streams work is fundamental to understanding Earth's surface processes, and it's critical for managing water resources and mitigating hazards.
Things that really stood out to me were how groundwater sapping works at the stream head, the sheer mind-boggling scale of those glacial floods, and how human actions like building levees can unintentionally starve deltas.
It's a dynamic system, always changing, always responding.
So hopefully you, the listener, have a much richer picture now. When you see a river, maybe you'll think about its journey, the work it's doing, the history hidden in its valley or its meanders.
It really is a story written in water and stone.
And a crucial question that emerges from all this, considering how dynamic rivers are and the growing pressures we put on them, is how can we actually ensure these vital systems remain healthy and sustainable for the future? Something to think about. And yes, that covers the entire chapter.